Piecewise functions today. You guys know what that is? Piecewise function? Give me 1 to 5 on that. When I say that word, how familiar are you? I'm seeing some zeros, maybe some ones. Okay, these are not high numbers. Okay, that's all right. So piecewise functions, we're going to maybe get to graphing some piecewise functions. I decided we're not going to do this. We'll just save that for calculus, and that's it. Okay. All right. So the most common application of math, I would say, is probably modeling stuff with math. So one example is projectile motion. Like I studied physics, which has a ton of math, but wasn't actually a math major. And physics is just all about using math to make predictions, to build models that describes the way the world works, right? So let's look at an example here of one way that we could use math to do something kind of interesting. Now, where did that go? No, where is that? There it is. Okay, I built some stuff here just for you guys to mess around with a little bit. I could make these available if you want to play with these later. We're going to look at some projectile motion stuff. I didn't build this. This is from I like these physics simulations. They're pretty cool. Okay, so what we've got here is we've just got a cannon, and we're going to try to figure out how we could aim this cannonball and control the speed. And we can also control the height of this thing, okay? So we want to try to be able to aim this thing so we hit the target, okay? Let's shoot. We're going to shoot pumpkins, I guess. And like if I shoot one out of here, here's what happens. Okay? So if I want to try to hit this target, I could adjust a bunch of things. I could adjust the angle and I could adjust the speed, right? So obviously I need to make this thing a little bit, the muzzle velocity, the speed with which the cannon's leaving the barrel needs to be a little higher. What do you think? Let's maybe tweak the angle a little bit here too. Anybody want to give this a shot? Tell me some numbers. Right now it's an 80-degree angle. Give me an angle and a speed, and let's see who can get the closest here. We'll have a couple volunteers. What do you think? Yes, sir. Jack, what do you got?
Let's go 6 degrees with 17.
Okay, with 17. We were at 11. We'll go 17. All right, that looks pretty good. Let's try that. Okay, not bad. Not bad. Okay. Anybody want to? Now, what do you think? Okay, yes, sir. Cole, what do you got? Cole, go ahead.
65.
Okay.
Same speed.
65 with the same speed. Okay, we'll try that. Ooh, close. Deacon, what do you got?
Let's go 70.
What was the angle again?
70.
Okay, 70. Same speed? Okay. I like you guys are doing a controlled experiment here, only changing one thing at a time. Ooh, that's pretty close. I think it kind of counts, but can we get even a little closer? What do you think, Adrian? What do you got? 75 and what speed? 15. Okay. And you want the speed slower? 65. Whoops. Okay. Yeah, I was wondering. There we go. Okay. 65 with 15, you said? Okay, let's try that. Close. Anybody else want to give this a shot? We got to get it at least once. What do you think?
Speed is 17 and angle is 68.
Okay, 17. We're going to go up to 68. Oops. Oh, man, look at that. Pretty good. All right. So I could make things quite a bit more complicated, though. Like if I were to pick this thing up at a certain height, is that still going to work? No, it's not, right? And we'd have to start all over again. We got to figure out, now we got to pick some new angle or new angles, new speeds. Wouldn't it be much more convenient if we could just calculate this, right? And know we're going to get it right on the first try? Okay, well, we can. We can do that. If we use, there are some math models we could use that I have built here. Here's just a little equation involved. It involves some trig. It does involve some stuff. But we could use physics here to control the parameters, so we could predict exactly what we need. And I can adjust. I've just built a little document here in Desmos graphing. You guys, I'd really like you guys to get used to using Desmos graphing, and maybe later in the year, you have a little spare time, like before winter break or something. Maybe we could do just a fun little project where you guys have to build something with Desmos graphing. The reason I think this is so good is because it uses math. I mean, it uses math in a way where it forces you to kind of take a different perspective on the math, but also it is the stuff you do when you build functions and you build, you're using variables, you define variables, which are sliders in Desmos. You can slide these values. This is just like coding. I mean, it's really the same kind of thinking that you use when you code stuff. And how many people have coded in? I think probably asked you this too. How many people have done some coding? Well, I mean, that's some, right? I mean, so like was it in Scratch or something? Is that what it was? Yeah. JavaScript. Okay, good. So I would strongly encourage you to do that. That is, and I think I already told you about this, but I'm going to keep on harping on this. Coding it's the skill that if you look at colleges in programs that are analytical, science, engineering, math, that's the skill that they value almost the most. I mean, math is probably the most important skill, but coding would be a second, just a close second on that. And we don't really offer much in the way of coding, so you're kind of on your own to do that stuff. I mean, there are schools where you have 2 or 3 different AP coding classes. We don't have the benefit of that, but it doesn't mean you can't do it, right? You can still. There are all kinds of places you can do that online for free. Yes. Signups for robotics club are open right now. Okay, and that you guys do some coding in there. Yeah. Okay. What do you code in there? What language? Just Java. Java. Okay. Yeah. And Java's a really good language to learn to code in. When you get to college, you'll probably, like, if you're in engineering, you guys will all learn to code in Python, and Java and C+ are kind of interchangeable a little bit. But there's all these, and once you learn one language, the rest of them are pretty easy to learn. But it'd be a really good idea to just get used to that a little bit, right? I think it's a very good idea. This is one footstep into doing that. If you can do this, coding becomes pretty easy. So we can just now in real time, we can adjust all these parameters. So the height of what did that look like? Well, the height was this thing, right? We move this pedestal up and down. The angle we're calling phi right there. That's usually we use like either a theta or a phi, these Greek letters for angles. And then the speed, I'm just calling s. And by tweaking those things, look what we can do. We can change, by changing the speed, we can see what the range is going to be on this thing, where it's going to land. I can go up there and highlight that point if I want to, right? I can change the angle. If I make it steeper, you can see what happens. What do you think the angle is going to be that gives me the maximum range? 45, yeah. Look, 45 is where it peaks. Right there. And if I go less than that, it gets smaller, or if I go greater than that, it gets smaller. I can adjust the height of the pedestal, and that has an impact, right? And in physics, what we would do is we would use these models, and we would actually create an equation and solve for the variables and figure out what is the optimum, like what are some values that would hit the target dead on, and it would work every time. Okay, we can do, here's another one I found from University of Virginia. They had kind of a cool little model set up here where you can control the velocity anywhere from 0 to 100 meters per second, control the angle, and it tells you what the range is. 255, how long it stays in the air. Okay, we can do all kinds of stuff. What happens, I don't want to spend too much time on this, and I'll put links to these if you want to mess around with them, but what do you suppose happens if I include air resistance? Let's see what happens. What's going to happen for sure if I include air resistance? Because all the models we've been dealing with so far ignored air resistance. So they would work on the moon, right? But they don't really work on Earth. What's going to happen if I do include air resistance? Not going to go as far. Yeah. And we can see that. Like, what if we set the initial velocity? We'll just leave them at 45. How about if I set the initial velocity at like 5 meters per second? Let's see what happens if we compare the range with air velocity to the range without air resistance. I mean, sorry, not air velocity. Okay, so with no air resistance, the range is 2.55 meters. Let's see what happens if we do include air resistance. It's the same. It didn't even change. Oh, hang on, I got to change the air resistance. What do I want here? What do I want here? I think. Okay, let's pick something like that. See what we get. The range is 2.54. Let's make it a little bigger. I can't remember what would be. Oh, here's some stuff. Okay. They have a golf ball. Let's do a tennis ball. Okay, tennis ball is about 0.019. So we want to do. So about that. That's similar to like a tennis ball. Okay. So if we shoot this thing at 5 meters per second with air resistance, we get 2.55. If we shoot it without air resistance, we get 2.55. It hardly even made any difference. So make a prediction for me. What if we shoot this thing with 100 meters per second? Without air resistance, we get a range of 255. What do you think is going to happen if we shoot it with air resistance? There's without air resistance. Okay, yeah, so what do you think? I mean, it didn't even, like when we shot it at 5, it didn't change it at all. Maybe this will change it a little bit, though. What do you think? Somebody give me a number. What was that again?
I was just saying because the range is like bigger, the numbers are like the air's I think more of a difference.
Okay, so give me, there's a good theory, good hypothesis. What do you think? Give me a number. If I add air resistance, it's a tennis ball. So we're dealing with the tennis ball here. If I shoot the tennis ball at 100 meters per second with air resistance, without it went 255 meters. Somebody throw a number out. What's it going to be with air resistance? Range. This is range. 243. Anybody else? 242. Oh, okay. Being strategic. All right, let's try it. Oh, I didn't hit. Whoops, got to hit air resistance. What did I? Oh, what's going on here? I feel like I'm doing something wrong. Can't remember how I. It's 0.19. That's the problem. Yeah, there we go. 0.19, not 0.019. Okay, let's try this again. Let's go back. Gosh, start over. Let's pick our initial velocity to be 5. Okay, so there it is with no air resistance. Let's do that first. Okay, they're about the same. 2.55 in both cases. Okay, didn't change much. Now if we go up to 100, without air resistance, 255, with air resistance, okay, not that much less, 253. Oh, I am, you're right. There's the problem. There's the problem. That's what you're getting at. Thanks. Yeah. So the range is little over 1,000, little over a kilometer, 1.01 meters. versus 1.02. So it's about 100 meters further, right? Okay, if the air resistance gets ramped up a little bit though, so what if we did like ping pong balls? Uh, I don't feel like this is right, honestly. Can I make this initial velocity like 500 and see what happens? No, it won't let me do it. Huh. Oh, here we go. That's what I wanted. This is the deal. Okay, what if we went 1,000 meters per second? That's what I wanted to do. So let's go 1,000 meters per second, no air resistance. And we're going out there pretty far. We're going out there about 10,000 meters. If I go with air resistance, look at that. Okay, that's what I wanted to show you. That's quite a difference, right? So what is the moral of the story here? Genevieve, you kind of hit the nail on the head. What's changing here? If I wanted to build a much more sophisticated model that's predicting the range of a projectile, if I'm including velocities, that was way more complicated, right? For low velocities, it made almost no difference, but for really high velocities, like if I'm going 1,000 meters per second, that's pretty fast. That's like a bullet out of a pretty high speed rifle. It made a huge difference. So what's the factor here that's determining whether there's a big difference or a small difference? The speed, yeah, right, the speed. And so what we're going to end up, we'll come back and revisit this later in the year, but what we're going to find here is that this is a non-linear model. It wasn't just like if we scaled this thing up, scaled the speed up, the ranges scaled up proportionally. That didn't happen. As we increased the speed, the ranges didn't change proportionally. They changed much more when the speeds were higher. So that's a non-linear relationship. It's not a line that's describing this. It's something more complicated. There's probably some terms in there that we call them quadratic terms, where the speed is being squared or where the speed is being cubed. So as the speed gets bigger, you get much bigger contributions of this air resistance, right? So all I'm really trying to get at here is that you can build these math models to accurately predict something like range downstream from the cannon. But it gets more and more complicated as you introduce more and more different types of parameters here, right? If it's in a vacuum, it's pretty simple. You introduce velocity, it gets more complicated, right? And there could even be some other effects that we haven't taken into account that might even tweak this a little bit more. This is what math does. This is what the job of math in the real world oftentimes is just to build these models so we can make these predictions. Okay, back to business. So what about something like this? We're going to start this section. We'll just kind of do a little, it's Friday, just kind of think about a little story here. Nice little story. How could we model this different, more complex situation? So imagine this experience while you're visiting the beach at sea level. You hitch a ride on a hot air balloon that rises vertically to an altitude of 15,000 feet, at which point you bail over the side of the basket with a parachute. You plunge downward until you reach an altitude of 3,000 feet where you deploy your parachute. Okay, describe that trip in detail. What are the different chapters in that story going to be? Every time something changes dramatically, we'll call that a new chapter. What's chapter 1? Okay, so period 1. Chapter 1 might just look like you're riding upward from sea level at a constant speed, let's say, right? That might take a while. I mean, if you're riding up in a balloon, it might take you an hour to get up to 15,000 feet. So that's a pretty long chapter in our story. What's chapter 2 going to be? Okay, you bail out the side. Describe what's that like? What's that going to feel like?
You're gonna be speeding up until you reach maximum velocity or deploy your parachute.
Okay, so the first, we're going to be accelerating, gravity is going to accelerate us, and we all know what that feels like, right? You've been in a ride at an amusement park or something, it's when you lose the floor or you jump off a high dive or something. That's kind of a weird feeling, right? You can feel the acceleration pushing you down. You're going to pick up some speed. That's not going to last very long. You're going to accelerate downward, not forever, right? What's going on, Caitlin? You already told us. You don't accelerate forever. You hit terminal velocity, right? If you accelerated from 15,000 feet to the ground, what would we could do a little calculation, but I'm going to estimate that your speed, if you didn't hit terminal velocity, you'd probably hit the ground going something like really fast. You'd hit the ground going many, thousands of feet per second. So it'd be real bad. Fortunately, though, you hit terminal velocity. It takes about 12 seconds in this case to hit terminal velocity. And then what? And at that point, you've fallen about 1,500 feet. That's about how far it takes to hit terminal velocity. Then what? What's the next phase? Okay, yeah, you're gonna. Well, not quite yet. Okay, we're gonna float down. We're not float. We're gonna plummet down to the ground at constant speed, right? Terminal velocity until we hit 3,000 feet. Okay, and if you're hitting terminal velocity, you can control that a little bit. Like if you were diving, you'd go typically about 180 miles per hour. If you're falling, kind of belly towards the earth, you about 120. So you're going to fall at a constant speed. That would take about a minute to get down to 3,000 feet. Then what do? Okay, yeah, you hit the ripcord. What's that going to feel like? You're going to get jerked pretty hard, right? That's gonna slow you down. So you're going to experience an acceleration. And what direction is the acceleration you're going to experience, or the force? Upward, yeah. So you're going to get accelerated upward, aren't you? And that's going to be fairly dramatic. And that might take about 3 seconds for you to get pulled strongly upward. And then what happens? Okay, so we're gonna float down, and we get a new terminal velocity, right? But this is a lot slower terminal velocity because the parachute is impacting that. Okay. All right. So if we wanted to, how are we going to describe all that in math? Like that's more complicated. With the projectile, it wasn't such a big deal because once the cannonball leaves the cannon, everything's the same, right? When it's in the air, we just have to come up with one math equation to represent that, which I showed you what that might look like. This is way more challenging. What am I going to do here? These are really dramatically different chapters in our story. How could I deal with this? Say it again. A lot. Well, it's even more than that. It's because parentheses, like if I had an expression that had some parentheses in it, it's still part of a single function, a single calculation, right? I've got to be able to break this up into separate parts. And one way I could do that is I could use something called a piecewise function, right? The piecewise function looks very different than the functions you've dealt with in the past. Piecewise function, there's our function notation, f of x equals, and then there's going to be this big script bracket, only one of them though. We've got this script bracket, and what that's telling us is, okay, there's going to be multiple rows here, multiple pieces in this piecewise function. Each row just corresponds to one piece in the piecewise function. So let's look at this one as an example, and then we'll kind of think back to that parachute example and think about how we could set this up. So what's this telling us here? This says f of x is equal to the top piece, the red piece, whenever x is less than or equal to -2. So for those x values, this is the function that we're going to graph, y equals 2x. Okay, that's a line, right? Line with a slope of 2, y-intercept of 0. What about when x changes, when x all of a sudden is not less than or equal to -2, when it's greater than -2, we flip into the blue piece of the function. Okay, that's where the equation that describes this piece is y equals -1 minus x. And that's the piece that's going to exist whenever x is between -2 and +4. Okay, when x is greater than -2 and less than 4, we're on the blue piece. And then again, when we let's imagine an ant is walking on this function from left to right. When the ant's x coordinate is less than or equal to -2, he's walking on the red line. When his x coordinates are between -2 and -4, he's walking on the blue piece. But as soon as he steps on +4 and moves further to the right, when x is greater than or equal to 4, now he jumps to the green function. So what's that going to look like? Literally, it's going to look like 3 separate pieces that correspond to different graphs, different lines. Okay, we could do something like that with our example here. How many pieces would our piecewise function have to describe this adventure we just had? Got to have 5, right? Now, if I were to graph this thing, what would be, like we were using, I guess maybe there was even one more there. What did I have? Oh, piecewise function, yeah. Piecewise functions just made up 2 or more function pieces, each with its own domain. So we were graphing, in this case, looks like a regular math graph in the xy plane. The input variable is what for this function? It's x. How do you know? How can you look at it and immediately know the input variable is x? Yeah, look right here. Because it's telling us f of x, right? That's function notation. And we'll go back and talk way more about function notation soon. But you guys have seen this. That tells us what's the variable we're inputting into the function to calculate an output, right? So our input variable is x. Our output variable is y. Remember, f of x is just a fancy name for y. I'm sure you've heard that before. For our previous example with the parachute, what do you think our input variable is going to be? What's determining here when we change from one chapter to the next? It could maybe be height. That's one way we could do it. What's another way? Time. Yeah, we could do time, right? We know how long we're doing each of these 3 parts, okay? The first chapter takes an hour, second chapter takes 12 seconds, third chapter takes a minute, and so on. What would the output probably be? What's interesting about this? What's the height? Yeah, the altitude's probably the output, right? So if I were to graph this thing, if I were to graph that piecewise function, it's going to look like something like that, right? Where we've got height in feet, I guess, and our input is time. And we could do that in, how about in seconds, I guess. It's going to be, times are pretty different. But what's this thing going to look like? Well, we're going to start off, I mean, we don't have to graph the whole thing, but we start off this first part where we're writing upward. It takes a long time. It's very slow. What's that going to look like? I start at 0, my height, right? And what do I do? Yeah, I just go up pretty slowly, don't I? Right? So as time passes, my height is increasing. I'm just going to go up like that, right? Eventually, I get to my highest point, which is 15,000 feet. And then what did I do? Well, let's see, then I bailed out, right? So I accelerate downward for a very short period of time. So that's going to be, what do you think that's going to look like? Okay, yeah, it's going to be close to straight down, isn't it? We're going to do something like, oops, I need green. Green, I said. Didn't order that color. Something like that. I'm picking up speed. It's getting steeper and steeper, right? The slope of this thing. Until I hit my terminal velocity, and then that's blue, right? I hit terminal velocity and I fall for a while. So now I turn blue. I'm going to go down pretty steeply for a while until I get to 3,000 feet, and then what happens? Okay, yeah, then I'm going to slow down really suddenly. What color was that? That was that, whatever that color is. We'll call it orange, close enough to orange, right? So then this thing is going to lose speed pretty quickly. And then the last step, I'm just floating to the ground at very slow speed. So it just continues on until I get to the ground. Right? That's what the graph of that piecewise function might look like. There are 5 distinct parts of that. And if we wanted to build that as a piecewise function, we would probably do something like that. F of t equals, I need to make room for 5 rows. And I don't know what the equations are here. We could figure some of this out, but that's really not the issue right now. We'll just call this first one equation 1. When is that happening? What's my domain going to be, right? The domain is the set of all the input values. You guys remember domain and range stuff? Okay, and we'll come back and talk more about that later. Again, that's kind of like next unit. We'll spend a lot of time on functions. But the values of x where this is happening are when t is greater than or equal to 0, right? Because we start at 0. And when did it end? After an hour. So we're going clear up. If that's in seconds, that's what's 3,600. So there's step 1, right? Step 2, we would have equation number 2. And the domain of that would be when t is greater than, we'll make that equal, greater than 3,600 and less than or equal to, what, how long did that last? 12 seconds, so 3,612, right? You see what I'm doing here? And we're just going to build this thing up so as t progresses, the ant's going to move from the red part of the graph to the green part of the graph to the blue part of the graph, etc. And we can just build the function that way. And it's what's great about this is this kind of function then, even though these are really different behaviors, we have a single function that can deal with all that at the same time. Okay, so let's go to a math one that's maybe a little simpler. Let's graph this thing. Okay, how could we graph this thing? What do you think? There's 3 parts. Suggestions. What would you do? And you probably can put the pieces together here. Any ideas? Remember, the red piece only exists in its domain. So where do I graph the red piece again for what x values? Less than or equal to -2. Okay, so then maybe we want to put some boundaries in here, right, to help us recognize when we're transitioning between the different pieces of this piecewise function. So one of those transitions is at -2, the other one would be at 4, right? So there's our vertical lines that are just going to separate the pieces of our piecewise function. The first one is going to be the red region, right? There's the place, every place to the left of this vertical line, that's the region where we're going to be graphing the red piece of the function. So now all we have to do now is just graph the red piece in that region. So how could we do that? We're just graphing the line y equals 2x because that's the piece that exists in the red region. I can graph that a bunch of different ways. We could use slope-intercept form, right? What's inconvenient about using slope-intercept form here? Like if I used mx plus b, the y-intercept is 0, right? And the slope is 2. That's maybe not the most convenient way to graph that line. How come? Say it again. Well, okay, like if I was going to use slope-intercept form, my y-intercept is at 0, right? And my slope is 2. So I get a point there. Well, yeah, those points define the line. Yeah, but they're not in the correct region, right? So if I'm going to do it that way, I would have to take this line and kind of draw it, go backwards, and then erase a part of it. Whoops. Erase the part of it that's not in the red region. That's not very efficient, right? We don't really want to do it that way. So what could we do instead? A point requires how many, or sorry, a line requires how many points to graph? 2. So I only need 2 points. So what would be a more convenient way to get 2 points out of this? Yeah, just plug in values that are convenient. I'm going to plug in x values that are in the domain of the red piece, meaning in the red region, right? So I could pick any values less than -2. Now I'm going to suggest that one of them is a particularly good choice to pick. What would that be? And this is not anything mathematical. I'm just thinking about like common sense problem solving stuff here. What would be probably a really important value to plug in for x? -2 would be great because we want to know where this thing ends at the edge of its region, right? So we could plug -2 in. And if I plug -2 in, I just get -4. So that corresponds to a point, right? -2, -4. So we've got a point, and it's going to be solid or open at -2. Solid's correct. How come? Okay, because the red region, look at that, the red region includes the -2. So we're going to pick a solid endpoint to use at -2, -4. So right there. Okay? Are we out of here in like 1 minute? Okay. Well, we'll pick this up next time. But you get the idea. Finish this up on Monday.